Fine, so let's do this new experiment today. That is finding the thickness of a sample using a wedge shaped film. Okay, so before we start the experiment, as usual, just 2 points about the experiment that what is this wedge shaped film? How do we get this bright, dark, bright fringes? Okay, so what happens is there is going to be two layers. There's going to be two layer of glasses. Okay, you'll have two layers of glass which will be almost parallel to each other, just that it will be little band with micrometer size thickness. Okay, because we'll put some sample inside. So what will happen is there will be a ray of light which will be falling on it, on top of it. Now whatever falls on top of it will be getting reflected back with not much phase difference, will remain almost same. But there will be another ray of light which will be also going through it. I mean, a lot of it. Okay, a lot of it will also go through it and bounce back. Some of it will just, which will pass through this glass and come down and it get reflected back. Okay, and get reflected back to the same position here. Okay, we'll undergo a phase change. We'll undergo a phase change. Okay, we'll undergo a phase change. So that phase change is going to lead to an interference pattern. Okay, it's going to lead to an interference pattern here. Okay, because there will be difference in the refractive index. Okay, because there will be air, glass, air in between and glass. Correct. Okay, there is air, then we'll have glass. I mean, this is glass, and then we'll have air and glass. So there's going to be continuous difference change in this refractive index, which will cause interference pattern, leading to dark and continuous dark and bright bands. Okay, so this is a very short thing about how experiment is going to work. So let's immediately go down to our experiment. The aim is to determine the thickness of a thin metal foil or a wire, where we have a very thin metal we given for this experiment. Okay, very thin, like a foil. It is like a wire also. All right, you can say whatever it is, by producing interference in the wedge shaped film. The apparatus, you'll need a pair of glass plate for it, a monochromatic source of light. The monochromatic source of light is sodium. Okay, magnifying lens, traveling microscope, sample any fine string or strip of micrometer thickness. Fine. The formula that you'll use is wavelength multiplied by the length of the air film and divided by 2 times the band width. All this is mentioned here. The value of wavelength is 5890. So setup, that is apparatus, is very similar to Newton's ring experiment. If you have seen my video on Newton's ring experiment, I've explained all this over there. Okay, so again, I won't go in detail about it. You can watch my video on Newton's ring. So we're having 3 scales on the traveling microscope. Okay, and this is the glass plate. As you can see, this is one glass plate here, and there's a second glass plate here, and if you can see, there's a fine wire on which is there inside. Okay, now this wire and this glass plate 1 and 2 are just kept parallel on each other, and we fasten it using a rubber band. Okay, so there is a edge here. There is an edge of glass, and this wire which will form the air film inside. Okay, it will form an air film length L. So this is that length L that we were talking about of air film. Okay, it will be from the wire up to this edge where the glass length ends. Okay, over each other. Okay, this is an extra length of one of the glass, but the second glass is just up to this point. Fine. This is the sodium source, and this is that glass plate, that same glass plate that we have used for Newton's ring experiment. Fine. Okay, setup is same to same, just that instead of lens we are going to place this glass plates, pair of glass plate with the sample inside. Fine. So this setup, this is the same photograph from Newton's ring experiment, so just ignore this lens which is kept here. So instead of lens we are going to place it with those this what we have here. Okay, we are going to place it with this one. All right, so same to same again. If you find anything missing in any explanation, then just go to Newton's ring video and listen to it. So same way I found the focal length of the magnifying glass. Okay, the magnifying glass is kept at the same distance as what its focal length is. Okay, And then instead of rings in the wedge shape film, what you get is bands. Okay, you can see this is the difference between Newton's ring experiment and wedge film experiment. Okay, so you get straight lines. Okay, and we will take readings of at least 10 alternate either dark or bright band. I have like to focus on bright bands because the crosswire, you can see this black color crosswire. Okay, you can see this black color crosswire, it forms a really good background with a bright band instead of dark band. Okay, so I will take around 1 2 3 4 5 6 7 8 9 10 band readings, and what we will do is we will subtract 1 from 6, 2 from 7, 3 from 8, 4 from 9, and 5 from 10. Okay, we will subtract each of the bands, so that will give us a very good average length of the bandwidth. We will get a very good bandwidth if we do this process. Okay, if we do this procedure, we'll get a very good bandwidth because we'll now then subtract from, because these are so close that you may get a lot of error. If you just subtract 1 to 2, 2 to 3, 3 to 4, 4 to 5, if I subtract like this, I will get a lot of errors. So what I'll do is I will subtract on a bigger distance, 1 to 5, 1 to 6, 2 to 7, 3 to 8, 4 to 9, 5 to 10. I'll subtract and I'll take an average of it, and then I will get a proper band width. Fine. I hope you have understood what we are going to do. So this is the ray diagram that we have. Okay, and obviously it's going to form a wedge film like this, wedge. The bands this way. Okay, and this is the air film length. Okay, which I've shown you in the picture that I had. Okay, how it is going to be. So that's the length. So this experiment has two parts, unlike Newton's ring, which you just find the diameter of the ring and that's over. No, here you have to find the distance of the band from, or measure the band from 1 to 10, and after that also find the reading for how much this thickness or how much this length of air film is in the wedge in that setup. Okay, so that's it. We now go to the laboratory to perform the experiment and come with the data and see what we get. Okay, and whether we can find the thickness of the wire or no. Fine, so see you after the experiment.
All right, so we have set the glass plates so that we could get the fringes, dark and bright alternate bands here. Okay, now it's not so clear on the webcam, but what we will do is we will focus on those bright bands from the edges side, because it is too bright in the middle. We cannot actually see the wedge very clearly. Even the reading on this is not so clear, but I will put a magnifying glass for you to see the readings. All that we need is 10 readings. Okay, we just need 10 readings. There is no left and right readings in this particular experiment, just 10 readings. That is what we want. So we will just go taking in any one of the directions. Okay, so the I'll see that the microscope moves in this direction so that I can get 1 to 10 readings in this direction. Fine. Okay, so there's nothing like left and right in this. Okay, just that top and bottom, so up and down reading of 10 readings that I want. Okay, so we will do that. All right, so I've already adjusted on one of the bright bands. Let me just do it again. Maybe, yeah, it's gone too far. Yeah, so this is already adjusted on one of the bright bands. So let me take that reading, and from there on let me take the readings for the next bright bands. Okay, yeah, so I've already adjusted on the one of the bright rings, so let me take that reading first. Okay, so here we have the 0th one already on 5 6. It's there on 6. Okay, and main scale is on 6, exactly on 6. Okay, and if I could show you the vernier reading. Okay, here is a magnifying glass. I will try to show you with the help of magnifying glass. Okay, so here is a magnifying glass and it's on 6, if you could see. Okay, 6 means 0.6. Okay, not 6 as this is 1 2, so it's on 0.6. Okay, so you have to take the reading on 0.6. So this is our first reading, 0.6. Okay, the least count of all the scales on the traveling microscope is same, so nothing to worry. Okay, so now I will move to the next bright band. All right, so I've already moved, okay, to the next bright band. So this is again on 0.6. So let me note it down, 0.6, and the vernier reading is 49. The last one I got 49. Let me move to the next bright band by looking at the end edges. Okay, I'll just take it using the edges. So let me go to the next bright band. There it is. Okay, so again it is on the main scale. Reading is on 0.6. It's still on 0.6. Okay, it's still on 0.6. And let me note down the vernier reading. Vernier reading is on 45. So let me note it down, 45. Again, let me move to the next bright band. All right, so I'm already on the next bright band. So the reading is 0.55, 0.55, and the vernier reading is 44. I move to the next bright band. And the reading is on 0.55. And the coinciding reading is 39. Next we have, I hope I can show you this. All right, so again, if you can just magnify this, yeah, you can see it's on 0.55. Vernier very difficult for you to see using this setup. Okay, but anyways, let me go to the next bright band. It is here. All right, so let me again take the next reading. It is 0.555. Again, I take 0.55, and the vernier reading is 28. Let me again move to the next bright band. So you must have understood it's a very simple experiment. Okay, very simple experiment. So going to 7th bright band now, and we are on 0.55 still, 0.55. And the coinciding is 3. Coinciding is 3. So 8th bright band we go to. Yeah, 8th bright band. And this is on 0.5 now. We are on 0.5. And the coinciding reading is 41. Coinciding reading is 41. Okay, I hope I can show you once again the 5 reading, the reading number 5. Here you can see 0.5 it is. Okay, exactly on 0.5. Next, let me move to the next second last reading that we need for this experiment. So the next bright band, very slowly. All right, so that's next bright band, and this is again on 0.5. And vernier reading is 38. And the last reading, let's go for the last reading. That's a 10th bright band. So 0.55, 0.5, I mean 0.5, and coinciding reading is 14. That's what I got, 14. So we are done with the 10 readings for the separation between the 10 bright bands. Okay, you can even use 10 dark bands, no issues. You can even use 10 dark bands or take 10 bright bands, but since the crosswire looks more clear on the bright bands, I've chosen bright bands. Next, what we have to do is we have this glass plate here. Okay, we have to find the distance between the crosswire, the wire where it is kept, to the edge of the glass plate. Okay, so we have to take the reading from the crosswire up to the edge. Okay, so we don't need this setup now. All right, we have to remove this. Okay, we have to remove this setup of glass plate, and now we have to only take reading from this wire up to this edge. Okay, we have to find out how much distance is there from this wire up to this edge. Okay, so we will do that now. All right, fine. So as you can see in the camera on top, okay, I focused on that wire. All right, and I will be taking the reading of the MSR and the VSR from here. Okay, I wish I could focus this using the camera for you, but I don't know whether I can do that. Let me just try it. It's quite difficult adjusting this camera on this scale. You can see something, but you'll be able to see it vertically. So let me just skip that. I will take the readings for you. Okay, I will take the readings for you and note it down. And I can see that the wire right now, the MSR reading is on 8.3, and the VSR reading is on, I need a magnifying glass. The coinciding reading, that's what I mean. It is on it's on 30, not 30, 42. No, this is 37. Okay, let me just note it down. It is 37. Okay, I don't know whether I can show you using, if I can detach the camera and show you here, and then keep a magnifying glass in front of maybe and show you the readings. Okay, this is the best I can do. All right, so I hope you can see it. All right, this is the best adjustment I can do for you for the scale. Fine. So now what I'll do is I will move this till the edge where this end is. Okay, and try to focus on the edge. Fine. And of course I have to move the camera and all, so I'll just do that adjustment and get back. All right, so now I have focused on the edge of the glass. Okay, from the wire to the edge of the glass, and now we should take the reading at this point. Okay, where the edge is. So let me note down the reading for you, and it is almost come to 0.75, and the vernier reading is 5. Okay, so let me just try to show you using the camera. Okay, so this is the best I could do. So this is what I've got. So this is the length I've got of the glass, of the air film that it was there in the glass, and because of which the wedge was formed. So we now go back with all this data that we have got, okay, to do the calculations, all right, of the separation between the thing, and we'll see if we can find the thickness of that wire that is given to us. Okay, if we have got our readings properly using all this setup that is done only for to make up for an offline practicals, then we should get it properly. Fine, so see you for the calculations.
So welcome back. We have now our data. Okay, as you, if you're following my video, you must have seen this data that we got. Okay, so as I told you, we are going to subtract 1 from 6 and so on like that, and we are going to get these band distance from 5 difference of 5. Okay, so what we do is just simply add them up and divide by 5 to get the mean band width. Okay, this is expected to be more accurate than these, each one of them, because they are very closely separated. Okay, I have explained you why we are taking 5 already. Do listen to it properly. In case you have just forwarded the video, then possibly you might have not heard about it. Then of course the length of the air film was found, and we have found it to be 7.5782. Okay, I think calculations are quite straightforward, nothing much to explain here. So let me just go to calculations. The thickness, which is equal to the wavelength, the length of the air divided by 2 into the bandwidth, and wavelength is 5890 into 10 raised to minus 8, multiplied by the length of the air, and bandwidth is 0.08. So what we get is 2.79 into 10 raised to minus 3 centimeter, which is nothing but equal to 2.79 into 10 raised to minus 5 meter, which is equal to 27.9 micrometer. So that's a very simple calculation, straightforward, nothing much to do or look for. Okay, so if you want to write the results, you can write this as thickness of the metal is 27.9 micrometer. If you want, you can even write equal to 2.79 into 10 raised to minus 3 centimeter equal to 2.79 into 10 raised to minus 5 meter equal to 27.9 micrometer. Okay, so that's the result. You can even use this technique to find the thickness of the hair also, if you have a good setup and a good darkroom setup. If you have, you can even use for hair to find the thickness of the hair. Of course, your hair will be just 1 digit before the decimal number. It will be much more thinner than the string that we have got. Okay, Fine. So with this, we have finished the experiment, and I hope you enjoyed it. And hoping to see you for some other experiments soon, hopefully offline, or at least online. Okay. So till then, thank you, and see you.